Okay, let's talk about factors that influence running economy. Remember, running economy is rate of oxygen consumption. The first factor that I want to talk about is running style. There's lots of ways to quantify running style. I'm going to just start by talking about the basic kinematic descriptors of running style, and that's stride rate and stride length. Stride rate is clearly the rate at which strides are happening. So how fast we're having the foot strike the ground. It's also known as stride frequency, and I am guilty of going between those two terms back and forth, and they mean the same thing. The unit for stride rate will typically be strides per second, which is the same as saying hertz. So when you're reading literature, you may see a stride rate in hertz. All that means is strides per second. Hertz pretty much means anything over time. So even a video rate of 30 hertz or 200 hertz, that's 200 frames per second. Sometimes you'll see strides per minute. So any strides over a particular period of time is stride rate. Stride length is how far the person's traveling from within a stride. So that would be meters per stride. And that's pretty common just to use meters per stride for stride length. So interestingly, when we use strides per second and meters per stride, the product of stride rate and stride length is running velocity. And there's just a unit analysis. So here I have strides per second for stride rate, meters per stride for stride length. The stride gets canceled out. This is the numerator, this is the denominator, and we're left with meters per second. Meters in the numerator, seconds in the denominator. So running velocity is the product of stride rate and stride length when we set up stride rate and stride length this way. All right, so now what happens when we run a given speed at different stride rates and therefore different stride lengths? Well, there's some neat work on this, and we've done some work, and I'll show you this in a bit. So I'm going to show you some data like this. This is VO2, and this should be a dot here. This is rate of oxygen consumption on the y-axis, and this is stride length on the x-axis. This is a longer stride length and a shorter stride length over here. So remembering that running speed is the product of stride length and stride length. For a longer stride length, that means this would be a slower stride rate. For a shorter stride length, this would be a faster stride rate to run the same speed. So be careful when you're looking at these type of data to see what's being presented down here on the x-axis. So if I bring you into the lab and I put you on the treadmill and I just say, let's pick a speed, doesn't matter what the speed is, 5 miles per hour. And I say, just go ahead and start running. You will select a particular stride rate and stride length for that speed, okay? You will just naturally select it. And we can measure that. And then I can say, okay, for running at that speed, you're going to select this stride length, and we call that your preferred stride length. Interestingly, it's really hard to get you to change that. And it's also, we would also call this your preferred stride rate if we had stride rate on this axis, okay? So you just naturally select it. Sometimes we call it self-selected, but in essence, it's a preferred stride length and a preferred stride rate that you're selecting. Well, now let's say we measure VO2 for running at that speed with that stride length and stride rate combination. It would be this much, whatever that much is. Maybe it's 20 mLs per kg per minute, doesn't matter. All right, now let's say you're running on the treadmill and I say, staying at this speed, 5 miles per hour. So this is a set speed, running 5 miles per hour. I say, okay, take a longer stride length. So a longer stride length would mean a faster stride rate to run the same speed. What happens to VO2? Whoops, it goes up. It goes up, it gets higher. You become less economical when you start moving away from your preferred stride length and stride rate in general. So what happens if we say, okay, now run the same speed, still 5 miles per hour, but run with an even longer stride length and therefore an even slower stride rate? Oxygen consumption continues to go up. All right, now let's go back to your preferred stride length and excuse me. Let's go back to yeah, just letting you run however you want to run, but now the same speed, 5 miles per hour. But now I'm going to say take a shorter stride length and therefore a faster stride rate. What happens to VO2, rate of oxygen consumption? It goes up. Well, let's do it again. Let's say take an even shorter stride length and an even faster stride rate, still running 5 miles per hour. VO2 goes up. So we get this curve that has a minimum, and that minimum is usually pretty close to the preferred stride length and stride rate. Not always, and sometimes we have to help runners adjust their stride rate or stride length to find that minimum, okay? But typically, we'll be pretty close to picking a stride length, stride rate combination that results in the minimum amount of rate of oxygen consumption. That's really cool and really neat to try to understand. Now, that being said, these changes in VO2 are not huge, okay? So then let me show you some data that we've actually done here at UNLV. Here's VO2, rate of oxygen consumption on the y-axis. Here's stride frequency. Okay, remember, this is just, we either put stride frequency or stride length down here. This percent of preferred stride frequency. So we just called preferred stride frequency 100%. And then we had subjects run with a faster or slower stride frequency. So if it's a faster stride frequency, this would be a longer stride, excuse me, a faster stride frequency would be a shorter stride length. A slower stride frequency would be a longer stride length for running a particular speed. And we had subjects run 3 speeds. 3.13 miles meters per second, 3.58 meters per second, 4.02. So I think it was like 6.5 miles per hour, 7 and 8 miles per hour, something right around there. All right, so we had them run faster. And a couple things that we can get, or a few things that we can get from this graph. Here's running 3.13 meters per second, preferred conditions, and then we had them run faster. Well, one thing, we told them to run 15% faster stride frequency, and actually they were not able to hit that all the time. That's really important. It's hard to change someone's running style. It's hard to change it. Same thing on this side. We wanted them to run at minus 15% the stride rate, but they only hit this number right here, which is about 90%. It's really hard to change someone's running style. But when we did change the running style, VO2 went up, either by increasing stride rate or decreasing stride rate. But look at the amount. It's not that much. Maybe 1 ml per kg per minute. Here, maybe 3 or 4 mLs per kg per minute. All right. So that's important, is that the rate of oxygen consumption is not that dramatically different for a change in stride rate. And these are dramatic changes in stride rate. So now we did it again, but we had them run 3.58, so we had them run faster. And there's that shape of that curve, almost that U shape, but look, it's a little flatter than this graph right here. And then we did it again at 4, so even faster, and this graph is pretty flat. So thinking back, what we should have done is also measured VCO2. And we'll talk about this in a little bit. But this is only VO2. What this is not picking up is any anaerobic contribution the system has to meeting the intensity of exercise. And maybe what's going on here is the runners were using more anaerobic metabolism as speed increased. But nevertheless, we've got these data, and this U-shaped phenomenon, it's sort of there, but not that really. But it does get flatter as we go faster. Interestingly, the preferred stride frequency increases just a little bit with speed as well. That's pretty common to see as well. So what we took from this is the range of VO2 that is impacted by changes in stride rate were influenced by speed. And in fact, staying near that preferred stride frequency, stride length, the preferred set of numbers, that was more important. It was harder to get people to move off their preferred conditions as speed increased. So staying near that preferred set of conditions became even more important as speed increased. So a few things here, just sort of summarizing some points. Stride frequency changed slightly with speed, sort of a U-shaped phenomena as expected. Little change in VO2 near preferred stride frequency. So this range of VO2 is really not that much here, but yet we can have some 5% changes in VO2, or excuse me, 5% changes in stride frequency, but not really a big impact on VO2. So staying near preferred stride frequency became more important as velocity increased. So if running style is not the only thing that's going to determine VO2, what else could be influencing running economy? So let's look at that. So one factor or another factor is muscle capacity to store energy and use elastic energy during running. That is, the muscle tendon forms more like a spring. I've mentioned this before, that if we stretch a rubber band, that rubber band wants to recoil and it wants to pull back in. That pulling is not metabolically costly. The rubber band does not have an energy system to do that. But the elastic property of muscle and the elastic property of tendon does allow muscle to be stretched and then recoil with no metabolic cost. And so the factors that affect running economy is what a factor is how well the muscle can stretch and recoil to our resting position, how well the muscle can be a spring. And these are just mechanical pictures illustrating that. What other factors influence running economy? Well, fitness and training do influence running economy. People do become more economical with training. So for example, you can see a 1 to 4% improvement without changes, 1 to 4% improvement in running economy without changes in VO2 max. So you can train someone, they can have the same VO2 max pre and post training, but yet for a submaximal speed, they may use 4% lower rate of oxygen consumption, 4% better running economy. Age influences running economy. Children are less economical runners than adults. I showed that graph earlier, but they do become more economical with age. Is that training? Is it weight gain? Is it running mechanics? Is it elastic properties of muscle tendon? There's lots of things that could go into that, right? And the other part of training, and this sort of goes along with age, is you do learn how to coordinate muscle contractions. And that can be helpful to running economy. Fatigue can influence running economy, all right? Fatigue being a general tiredness. Running economy is worse with fatigue. So let me show you some data here. This is rate of oxygen consumption on the y-axis. This is stride length on the x-axis in meters. This is the preferred stride length right here. And these are data from my dissertation, where what I did is in the square boxes, in a non-fatigue state, I had people repeat that experiment where I had them run the same speed, but with a longer stride length and with a shorter stride length. Excuse me. And we see that pretty much a U-shape type curve. We see greater VO2 for longer stride length compared to preferred. Not too much change in VO2 here, and that's important to remember. Some subtle changes in stride length probably do not negatively influence VO2. So that's in the non-fatigue state, that curve right there. Then I had subjects do 2 different fatigue protocols on 2 different days. The first was I had them do a graded exercise test. And then immediately at the end of the graded exercise test, when they were exhausted, they straddled the treadmill belt. I changed the treadmill settings right back to the same speed that we tested them in a non-fatigue state. So this was at 8 miles per hour. They ran 8 miles per hour again, and this is how much oxygen they consumed after the graded exercise test. So they did the graded exercise test, had them stop and get the treadmill back to the original speed, and then tested VO2 again. And you can see they selected almost the same stride length after that graded exercise test, but yet they had a huge change in VO2. So system fatigue influenced running economy. They were less economical after the graded exercise test than before. So then did another test. So on a different day, I had the runners fatigue their quadriceps. So I had them sit down on an exercise machine and I had them do repeated knee extension exercises to the point where they could not do it anymore. And then I had them do it again and again. And I had them actually really sort of trash their quadriceps. And then I immediately after that quadriceps fatigue protocol, I had them run the same speed as in the non-fatigue state. Those data are right here. Interestingly, after only the quadriceps were fatigued, they picked the same stride length and therefore same stride rate as the non-fatigue state, and VO2 was not influenced by quadriceps fatigue. So system fatigue, VO2 went up, they became less economical. Quadriceps fatigue only, no change. All right, so let's see. All right, so so fatigue, system fatigue does influence running economy, but local fatigue did not, interestingly enough. All right, gender can influence running economy, but it's probably more related to body composition than actual gender. So maybe women can be considered more economical if body composition is more controlled. Ethnicity, maybe a factor, but really what's important is when people talk about ethnicity, there often needs to be a cultural understanding, maybe socioeconomic understanding of what's going on with different ethnicities. So for example, Noakes talks about this, African pygmies were about 10% more economical than Caucasians when running, but not when walking. And the question is that because of a culture, or is that because of an ethnicity explanation? So just be careful and make sure that you exhaust all possibilities before going with ethnicity as a factor. Factors that affect running economy included added weight. So if you run with a backpack, or if you run with weights in your hand, or if you run with shoes that are heavy, that will negatively influence running economy. So adding weight distally versus proximally has a greater negative effect on running economy. So having weight near the end of the feet or on the feet, near the end of the lower extremities, that can have a bigger impact than wearing weight around the waist. All right. This is actually a factor when we're talking about hydration later on. If we wear a hydration belt where we have fluid, we're carrying a water bottle on our waist versus carrying a water bottle in our hands. It's less economically costly if we wear the weight near the waist versus holding it in the hands. Well, likewise, shoes that are heavy are going to influence running economy in a negative way. So about 1% increase in running economy in rate of oxygen consumption for every 100 gram added to the shoes or to the feet. All right, and spring boots, running as a Pac-Man, I don't know. And orthotics can weigh about 80 grams, so we just need to be careful when we start inserting things into the shoe. We typically want them to be as least weight as possible to have the least negative effect on running economy. And same thing, racing flats are typically built to be as light as possible so that there's a less of an influence on running economy. That's the concept, at least. Other factors that influence running economy, environmental conditions, running uphill, obviously, about 2.6 mLs per kg per minute per 1% increase in grade. Running downhill can influence running economy. Running surface, if we run in sand or snow or any soft surface, grass, we can have a worse running economy. There's some neat work on trying to figure out if you can tune a track to a particular person to optimize their running economy. Pretty challenging because you would almost need a track for every person because it might be a little different for each person. But environmental conditions influence running economy. Wind also influences running economy. This is just the equation for drag force. Not really critical for this class to know this equation, but the greater the speed, the greater the drag force. Greater the speed hitting you in the face if you're running into a headwind, the greater the drag force. And different things can influence that drag force, including clothing that you're wearing or what size you are, or whether you're running behind someone. You can actually gain an advantage, especially running into a headwind, if you're running right behind someone. So follow within 1 meter. So you draft off a person, you run off their shoulder, if you will, especially into a headwind. And you'll be more economical than they will be. This is sort of a crazy graph. I'm not going to go through it, but summarizing this graph, the wind and the grade influence running economy, influence the amount of oxygen needed to run a particular environmental situations. We know this from ACSM. This is just the ACSM equation, and that you have to account for VO2, grade, when trying to calculate VO2, rate of oxygen consumption. Pacing does influence running economy. It's important to recognize that velocity is not constant during marathons for most people. Of course, the elite runners are trying to sustain the same pace throughout the entire race, but in a marathon where it's run outdoors, the pace will vary based upon environmental grade situations. If it's on a track and it's a little different, then it may be strategic changes in pace may be happening. Pace varies relative to elevation. Going to an aid station, you may slow down to maybe grab your aid, whether that be water or some type of drink or something to eat. Maybe weather changes during the course of an event. You have to account for that. Nutrition, fatigue. We actually looked at pace changes during different marathons, and we were able to quantify how pace varied based upon finishing time, and that was actually pretty neat. All right, so suggestions to improve running economy. Well, focus should be on improving running economy versus VO2 max. As mentioned, you can have an improvement in running economy. You can have a less rate of oxygen consumed for a given speed with training, but no change in VO2 max. All right. So training can improve running economy more so than VO2 max. Training increases the running speed at the lactate threshold. All right, we got to get in, and we'll talk about lactate threshold in a little bit. But if we can push off, we can delay the production of lactate threshold. That seems to be a good thing in terms of running economy. I'm not going to, we just need to be careful, because I'm not going to say lactate is causing fatigue. Lactate, we're going to actually look at lactate a little bit differently than the classic model of physiology. So training can increase the percent VO2 max that can be sustained, and that's a good thing. Noakes hypothesizes that rate of heat accumulation is reduced with training. That is, you become more economical and you're generating less heat. And that less heat is going to be really important. Later on, we're going to talk about the central governor model relative to core temperature, and that there might be a thermostat that the brain is detecting and starting to shut things down if core temperature starts to get too high. So it's not clear what training program is best to improve running economy. That could be influenced by the type of drills that someone does, improving coordination of muscle, as well as changes in physiology, how much, that mitochondrial density, the blood flow to muscle, and even maybe influencing the elastic behavior of muscles and tendons via plyometrics type of exercise. Practical suggestions for improving running economy: minimize shoe weight, minimize clothing weight, and even aerodynamics. Use tight-fitting clothing. cut down on the drag force that you have to overcome while running. Okay, summary of part 2 as running economy in total. Sort of broke this into 2 parts. Running economy and energetic cost of locomotion was the first part of this. And you need to be able to distinguish between those 2 terms and distinguish between running economy and VO2 max. VO2 max is the endpoint of a graded exercise test. Running economy is rate of oxygen consumed for a given speed. And then just going through factors that influence running economy. Okay, thank you.